Alright, so 4.5, day number 2, linear approximations. You'll be able to approximate any function using linearization. Review of differentials from yesterday is we've got right here. So you'll see we've got x and our x plus delta x, right? Some interval, which we call dx, which is equal to delta x, and our tangent line, right, which gives us an approximation for the change in y, which we call dy, where the actual change in y we call delta y. Alright, so we're going to find the equation of the tangent line today, alright, which we've done many times before, and we're going to use that. So, whoops, double lightsabers again. Consider the function here, right? What is the ordered pair at x equals a? Well, we know that that ordered pair is a comma f of a. My stylus is being funky. What is the slope of the function at x equals a? Well, that'd be f prime of a. So the equation of the tangent line would be y minus some y value, which we call f of a, equals the slope f prime at a times x minus that x value. This is called linearization, or it's the beginnings of it, right? We'll fully linearize this when we're going to call y L of x. It's a linearization for f of x. So all that we'd do is we'd solve for y, which would then mean that L of x equals, we're going to add f of a to both sides. And now we've got a linearization of f of x. Okay, so it's going to give us some approximations. It's not going to be perfect, but it'll be close. Alright, so find the linearization for f of x equals square root of x at x equals 100. Alright, I'm going to go ahead and sketch this off camera. I'll come back and look at it. Okay, great. Alright, I guess I'm going to do this without seeing the whole thing. The red graph here, as you can see, is the square root of x. And here is the tangent line, which we're going to call L of x, the linearization, right? So the slope here would be the derivative with 100 plugged in. As we know, the f of 100, which would be the square root of 100, is 10, right? So we know that the square root of 100 is 10. What we want to do is we want to approximate it in a moment using this linearization. So this function, right, f of a, well, that'd be f of 100. So that would be 10 plus the slope at a, which would be the slope at 100, which would be 1/20th, times x, which would be written like this, minus 100. So if I want the linearization, right, of, let's say, I don't know, here 101. If I want the linearization or an approximation of the square root of 101, I'd take 10 plus 1/2 times 101 minus 100, and I believe that comes out to be 10.05. Okay, same thing here. If I want an approximation of 99, I take 10 plus 1/2, 99 minus 100. So that comes out to be approximately, I think it's 9.95. Okay, so what did I do, right? I used different values for x in this linearization to estimate, right, or to see, whether or not, this line, this linearization would be a pretty good representation around this value 100. So let's see what we actually get using our calculator for the square root of 101 and the square root of 99. Okay, the yellow values there are actual calculator values. It looks like our estimates are overestimates, and that would be because if you check out what is going on here with our linearization, it is always greater than or equal to our function f of x. Alright, and part of the reason is because this function here is concave down. This slope will always be an overestimate, right? This linearization will always be an overestimate of that function. So it looks like our error between the linearization values and our actual calculator values are definitely within 1/100th, so that's pretty darn good. And that's just due to a small change in x there, dx of 1. And it depends on the function, whether or not a dx is small enough to get you within a certain amount of error. Okay, here we are. Let's go ahead and start on this AP problem right here, example 2. Approximate the value of y equal to square root of x squared plus 3 at x equals 1.04 obtained, that's spelled wrong, from the tangent to the graph at x equals 1. So recall that in order to get the linearization, I need f of a plus f prime of a times x minus a, and a in this case is equal to 1. Okay, so f of 1. So let's do f of 1 real quick. If I plug a 1 in here, it looks like I get square root of 4, which is 2. I do have to find the derivative. So f prime of x. Okay, I'm going to use a little chain rule action. That'll be 1/2 x squared plus 3 to the negative 1/2, right, using the power rule. And then using the chain rule, I'd multiply by the derivative of the inside. So f prime of 1 would equal 1/2 times 4 to the negative 1/2 times be 2 times 1, which is 2. So these 2's here will cancel, and 4 to the negative 1/2 power is equal to 1/2. So the linearization would be f of a, which is f of 1, plus the slope or the derivative at a equals 1, which is 1/2, times the quantity 1.04 minus a, which was 1, and therefore I've actually already done this. Right? That shouldn't be in terms of x, that should be terms of the input, 1.04. If I simplify that out, the linearization would give me an approximation, which would be 1/2 times 0.04 plus 2. It looks like I'd get 2.02 as my approximation. So my answer would be B. Alright, let's move on to the next one. Let f be differentiable functions such that f of 3 equals 5 and f prime of 3 equals negative 2. If the tangent line to the graph of f at x equals 3 is used to find an approximation to a 0 of f, that approximation is what? Okay, so first of all, let's just write the linear approximation. That'd be f of a, which is 5. We're going to say a equals 3. Okay, plus the slope x minus a, which again is 3. Okay, so we just need to determine x then. So we want to know an x such that we approximate a 0. So we want this function to cross the x-axis, which means we want y to equal 0. I don't know why I keep putting plus a negative there, but we'll fix that in a moment. So we want 5 minus 2x plus 6. So it looks like negative 11 equals negative 2x. So x would equal, looks like 5/2. Wow, good math. Try maybe 11 halves. Try 11 halves, which would come out to be 5.5. All right, there we go. B again. Okay, so here we've got another AP problem, non-calculator. So the volume of a spherical hot air balloon expands as the air inside the balloon is heated. The radius of the balloon in feet is modeled by a twice differentiable function r of time t, where t is measured in minutes. For the time between 0 and 12, the graph of r is concave down. So the table above gives selected values of the rate of the radius of the balloon over the time 0 to 12. The radius of the balloon is 30 feet when t equals 5. That is my first piece of important information. Okay, I've got a point. So estimate the radius of the balloon when t equals 5.4. So we're going to use linearization at 5.4. We know f of 5 is 30, and we actually do know the slope. Okay, we do know the slope as well. At 5, our rate, or our feet per minute, for that change in radius is 2. So if I want 5.4 estimated, oops, that's 5.5. How about 5.4? I'm going to plug in a 5.4 here and here. Okay, so my linearization, I did a little work on the side and didn't realize it, would be 30 plus 0.8. So it looks like the approximation would be 30.8 feet. Would this be, is your estimate greater than or less than the true value? Okay, because we know that this is concave down, right? If our original function is concave down and our tangent line approximation, L of x, looks like this, then what we know is that the values along that curve anywhere will be greater, so this would be an overestimate. So is your estimate greater than or less than? I'd say greater than, due to the fact that it's concave down. Alright, so I accidentally paused that, but my linear approximation will be f of 1 times f prime of 1 times x minus 1. Okay, I simplified that out here and then plugged in a 1.2 to do my approximation. Okay, so that approximation comes out to be -3. Okay, I'm told that f double prime right here is greater than 0 for all values between -1.5 and 1.5. So if that means our function is concave up, so our linear approximation would be an underestimate. Not well written, but you get the point. All right, that is 4.5, day number 2.